on? Is the microphone on? Are you working this time? Awesome. You say you're working, you better work. So actually, this is the third time I've recorded this homework session because the last time my voice didn't record. So that's fun. I'm going to go through, probably put this video into two parts. I'm going to do the first 18 questions, which takes about 20 minutes. And then I'll do the rest of the questions in a second video so that my computer doesn't die and that I have any chance of getting this stuff up to YouTube tonight. So the first thing that we're going to look at, I'm going to change my color. At least I have an option to change my color. I'm going to use black for this pencil tool, and we're going to go back to the hand. So in this problem, for problems 1 through 4, we want to give the vertex set, the edge set, and list the degrees of each vertex. So the vertex set here is V equals A, B, C, D, X, Y, and Z. The edge set equals AX. Now you have to list that twice because it's there twice. AY, BX, BY, XY, and DZ. Now, always put the squiggly lines because that tells us it's a set. So list the degree of each vertex. The degree of A is 3 because there's 3 edges coming out of that. The degree of B is 2. The degree of C is 0 because there's no edges coming out of it. The degree of D is 1. The degree of X is 4 because we have 1, 2, 3, 4. The degree of Y is 3. And the degree of Z is 1. Now, remember, every graph must have an even number of odd vertices. Here's an odd vertex, here's an odd vertex, here's an odd vertex, and here's an odd vertex. We have 4. That's okay. Okay? Problems 1, 2, 3, and 4 are the exact same. Just to reinforce a concept, I would like to go back to problem 1. Please stop doing this to me. Okay. Just to reinforce a concept here, this is a disconnected graph because it's in many pieces. Okay? And an example of a connected graph is in our homework. Number 4 is a connected graph. This guy is a connected graph. I would also like to draw your attention to the degree of vertex B in this problem. A loop always will contribute 2, so the degree of vertex B here is 4. Okay? That is something you absolutely need to remember. Problem 5, we're going to consider the graph with vertices K, R, S, T, and W. Okay, the edge set, I'm going to just go ahead and draw these in. RS, RT, TT, TS, SW, WW, and then WS. So that's one way you can draw the picture, and I'm going to just rearrange these vertices in another way because it really doesn't matter where you put the vertices, just as long as the edges that need to be there are there. So I'm going to go K, R, S, W, T. These are going to be the exact same graph. So RS, RT, TT, TS, SW, WW, WS. These graphs are the exact same graph, they just look different, okay? Does not matter where the vertices go, it matters where the edges are connecting them. Next, 6 is the exact same. I'm not doing that one too. You get the point. 7, there were questions on 7. There's always questions on 7. So, oh, Toothless, hi, hello, I need you to move. Please, I need you to move. You're not helping. You file this under not helping. Excuse me while I get attacked by my cat. Ow, you're hurting me. He wants attention. You're hurting me. Please get down. I just had injections. Thank you. All right, so where were we? Problem 7. I hope I'll remember to edit out getting attacked by my cat, but I make no promises. So sorry, that's distracting. It's distracting on my end too. I will make you into a scarf. Get down. Get down. I love you. I want to spend time with you. I want to cuddle with you, but I can't do that until I'm done with this. Thank you. So I want to list all the vertices adjacent to D. So that means all of the vertices that have all the edges that have D in them. We're going to try and figure out which vertices are adjacent to D. So A is connected to D. B is connected to D. D is connected to itself, and it is also connected to E. Edges adjacent to BD means anything with a B or a D in it. So we have AD is connected to BD. AE is not. BC is. BD is not adjacent to itself. If it was there twice, it would be, but it is not. DD is connected to BC, and then DE as well. The degree of D is how many times D shows up in this set. Shows up 5 times. So the degree of D is 5. The sum of the degrees of all the vertices. So let's find out. I'm going to zoom out a little bit. No, I don't want to go all the way back. Stop being a pain in my butt. Come on. Okay, so the sum of the degrees of all the vertices. So let's find out what the degree of A is. Remember, now I want you to keep in mind that there are 6 edges here. Okay, so the degree of A is 2. The degree of B is 2. The degree of C is 1, because it only shows up once. We know that the degree of D is 5. The degree of E is 2. So we know that 5 and 1 are our odd vertices. They're paired. Odd vertices will always be paired. Remember, there was always an even number of odd vertices. We will get into why in part 2 of this video. So the total here, the sum of all the degrees, is 12. Now, in problem 8, we explore this. There's a pattern here, and we explore it. But first, I want to talk about the degree of y. The degree of y is a loop. Remember, that's counted twice. So the degree of y is 1, 2, 3, 4. One of the most common mistakes made on this problem is not counting the loops right. Okay? A loop has 2 ends. Okay? Knowing what you know from the last problems, can you determine a rule for graphs and their degrees? Hint, how many degrees does each edge contribute to the total sum? Well, remember that edges cannot exist without vertices, but vertices can exist without edges. Now, an edge has 2 ends, and those ends have to go somewhere, whether it's in the same place or in different places. There is always 2 ends to every edge. Those ends are degrees. Okay, so the sum of all of the degrees of all of the vertices is equal to 2 times the amount of edges. And that means it will always, always, always be even. The sum of the degrees of all of the vertices will always be even. Always. Always, always, always. Okay? Toothless, stop being a spaz. I love you. Go away. You're distracting. Thank you. So 9 is a commonly asked question. 9, we're asked to give an example of a connected graph with 6 vertices such that each vertex has degree 3. So 1, 2, 3, 4, 5, 6. I want a connected graph, so I know it's got to be in one piece. So I'm going to go ahead and force that to be in one piece. Now your picture may look different than mine, and that's okay, just as long as it meets the criteria. Now each vertex here has degree 2, but if I start adding edges, these guys have degree 3, this has degree 3, this one has degree 3, this one has degree 3, and I'm going to go across here. That has degree 3, that is degree 3. That one's done. Now if I wanted to do a disconnected graph such that each vertex has degree 2, I can do this in many different ways. I'm just going to go ahead and give myself 6 loops. You can do it with 3 sets of multiple edges, or however else inspiration strikes you. A graph with 6 vertices such that each vertex has degree 1. There is no other way to draw this than disconnected. It looks like this, or it could look like this. Either way, they can even crisscross. Like, that would probably be super distracting because you might think that that needs a vertex there. So we might want to avoid this. Try and be neat in our drawings. So now let's move on to problem 10. We've done that. That's the exact same thing as problem 9. Let's look at problem 11. Give an example of a graph with 5 vertices such that each vertex has degree 3. Can't do it. That's an odd number of odd vertices. No matter how much I try, I can't do it. If I have 5 vertices with all degree 4, I can absolutely do that. It looks something like this. 5 vertices all of degree 2 looks something like this. Okay, can't do it. Odd amount of odd vertices. Amount of odd vertices. Okay. Let's look at problem 12. Give an example. Well, all right, fine. I'll just do 14 because 12 and 13 are very much like 14, but 14, it forces you to think about a disconnected version and a connected version. In the future, you will need to pay attention to whether or not I say disconnected or connected. Give an example of 6 vertices. 1, 2, 3, 4, 5, 6, where 3 of which have degree 1. 1, 2, 3. These bag got 1, 1, 1, 3. These 2 also need to be degree 3, so I can just do that. Now I want to do it connected. I'm just throwing them anywhere. So I'm going to start here because these guys all have degree 2. Now that has degree 3. This has degree 1. This guy has degree 3. This guy has degree 1. This guy has degree 3. This guy has degree 1. Okay? Your pictures could look much different. As long as they meet the criteria, I am happy. So that's 14. 15 we can skip. 16 we can skip. Those should be straightforward. If you need help, email me. 17. 17 causes trouble for everybody because people have a tendency to overthink it. So I want 6 vertices. It's connected. It's in one piece. I want 2 of them to have degree 1. Here, I want to have 3 with degree 1. Hi, Mr. Smokey. I'm going to tell you what I told Toothless. You need to go away. You're distracting. I want to cuddle you, but you cannot be here right now. Also, I seem to have mentioned my cats in a whole bunch of videos and never even posted a picture of them. I will make sure I do that in the announcements when I let you guys know this video is up. Because I think you deserve to know the troublesome threesome, the terrible threesome that plagues me on a daily basis. I'm kidding. I love them dearly. All right, 4 vertices. 1, 2, 3, 4. They have to have degree 1. We need 6 all together. Every edge is a bridge. These are types of graphs that we call trees. And then this guy is a special kind of tree that we call stars. You will explore the properties of these in an upcoming group work assignment. Okay? But every edge is a bridge. There are no cycles in it. Keep looking at that. So we're edging out on almost 16 minutes. So I'm going to cut this video off at 20 again, because this is recording 2 of 3 attempts tonight. These for 18, A, B, all of these should be pretty self-explanatory. Although when I'm asking you for cycles, there are ones that don't have cycles, like the cycle of length 5. It doesn't exist. Okay? No cycle of length 5. In this graph. There are other graphs that they will exist. Hey, psst, not right here. No fighting right here. If you're going to play fight, you need to go in the other room. Thank you. Hey! Psst. Don't hiss at me. I'm Mom. Shoo! Both of you. Separate corners. You can find the cycle of length 4. This is the same picture, so I'm just going to draw on it. There's a cycle of length 4. And here's also another cycle of length 4. That loop is legit, okay? You can use that to create your cycles, but there's still no cycle of length 5 in this graph. 19, list the bridges. I'm going to erase this right now so we can do that. A bridge is an edge who will disconnect the graph, okay? So here, EF and AH are bridges. Here, BF and FG are bridges. Vertices at degree 1 will always be adjacent to a bridge. Because if we deleted that edge, that vertex would become an isolated vertex. Okay? Remember this fact for later on. And I'm going to go over these questions, and then we'll restart the video at problem 20, because these questions deal with bridges. So I'm going to draw these out. These are okay to draw out. I don't mind. A, B, C, D, and E. A, B, do. None of these are bridges. No edges are bridges. Because if I remove this edge, I still have a picture that looks like this. Or not. A, B, C, D. Oh, I erased the wrong one. Come on. Do this right. This would be C, this would be D. So that has to be B, that has to be A. All right, now so this is D, this is E. I was right. Okay. So that would still be connected. So there are no bridges. Here, all of the edges are bridges. A, B, C, D, E. A, B, B, C, B, E, C, D. All of these guys are bridges. Because if I remove any of them, it would break apart this graph in different ways. These guys are the exact same. I'm going to save this recording and start getting it on YouTube post haste.